At 5:01 hours, with the freezing pre-dawn darkness still blanketing southern Russia, a 5-pound FPV drone initiated a final approach over Taganrog that would be over in seconds. On the ground, a Panzer S-1 defense system erupted, unleashing a barrage of 30mm shells at a rate of nearly 4,000 per minute. The drone's target was a hangar door scheduled to remain open for a mere 12 seconds. Inside rested a 195-ton Tu-95 MS, a $45 million strategic bomber and a cornerstone of Russia's nuclear deterrence. This engagement highlighted a stark paradox, a cheap plastic drone determining the future of a massive Cold War-era vessel built for global conflict. The actual target of the operation was not the sky above southern Russia, but the ground below it. The Beriev aircraft plant sat quietly near Taganrog as one of the most sensitive pieces of Russia's long-range military system. Located roughly 50 miles from the Ukrainian border, this facility was responsible for upgrading and extending the service life of the Tu-95 MS fleet. This aircraft remains central to Russia's nuclear strike planning despite its origins in the Cold War. Inside its hangars, aging bombers were reinforced, rewired, and prepared to carry cruise missiles capable of traveling thousands of miles, meaning any damage to this site would echo far beyond the factory fence. For years, Beriev was treated as a hardened node in Russia's strategic network, protected not just by concrete walls but by layers of technology designed to stop threats long before the human eye could see them. The outer shield of that protection relied on the S-400 air defense system, a platform designed to detect and destroy aircraft and missiles at extreme distances. Its large radar arrays scanned the airspace continuously, filtering civilian traffic from military objects and watching for patterns that suggested an incoming strike. Around this system were powerful electronic warfare units emitting overlapping fields of interference designed to confuse navigation signals and disrupt communication links. In theory, anything approaching Beria without permission would be detected, tracked, and neutralized long before it reaches the city. This defensive architecture created a sense of confidence that the site was untouchable. Over time, however, that confidence shaped both the hobbits on the ground and radar coverage in the sky. That confidence hid a weakness that no missile battery could fix, because the most critical barrier protecting the hangars was not a weapon, but a routine security system. The doors sealing off the aircraft were controlled by a digital access panel that still used a factory default password, unchanged despite years of escalating threats and repeated warnings about cybersecurity risks. It was a simple oversight, one that looked harmless during quiet shifts and routine maintenance cycles. Yet it opened a narrow path straight into the heart of the facility. In modern conflicts where advanced weapons rely on human procedures, this kind of administrative error can render layers of expensive defense ineffective in seconds. The Beriev plant did not fall because its weapons were weak, but because a small human decision was left uncorrected. This vulnerability was significant because it enabled planners to think differently about how to approach the target, shifting the focus away from brute force and toward deception and timing. Instead of overwhelming the defenses head-on, the operation aimed to slip through the gaps created by habit and routine, using speed and confusion rather than firepower. The objective was not to destroy everything in sight, but to reach a specific space inside the factory at a precise moment when machines and people were least prepared to react. That concept shaped every step that followed, from the launch location to the flight profile, and it transformed the Block C coastline into a quiet staging ground for a very different kind of attack. At precisely 5 in the morning, 20 FPV drones lifted off from the Ukrainian coastline and began moving south toward the Sea of Azov. Their departure was almost silent, with small electric motors pushing lightweight frames into cold air that hovered just above the water. Each drone stayed close to the surface, flying at an altitude of around 30 feet, where waves and reflections blended into background noise for long-range radar systems. By hugging the sea, the swarm took advantage of the Earth's curvature, which naturally limits the range of radar at low altitudes. This was not a high-speed dash, but a controlled glide designed to remain invisible for as long as possible. The environment immediately worked against the machines because the air temperature sat near 23 degrees Fahrenheit, a level that drains lithium polymer batteries far faster than usual. Cold increased internal resistance inside each cell, forcing the motors to draw more power to stay stable. Operators had to push the throttles harder to keep altitude, knowing that every extra burst of energy shortened the drone's usable flight time. The wind coming off the water added another layer of difficulty, nudging the lightweight frames off course and requiring constant correction. In these conditions, even a minor error could send a drone into the sea before it ever reached land. Software compensated where hardware struggled, and this is where the operation separated itself from older methods of uncrewed flight. Rather than flying in straight lines or rigid formations, the drones followed a control model based on biomimicry, copying the irregular movement of seabirds feeding near the coast. Their paths curved and drifted with the wind, rising and falling slightly as if responding to natural air currents rather than digital commands. To an observer watching through thermal sensors, this behavior blended into the typical patterns of wildlife that frequent the Sea of Azov. What initially appeared chaotic was carefully designed, and the lack of symmetry helped conceal its intent. This disguise proved effective as the swarm crossed toward Russian-controlled airspace because monitoring crews were trained to ignore minor erotic signatures that matched known animal behavior. The drones did not trigger immediate alarms, and no urgent response followed their movement across the water. Instead, they passed through the outer observation zone as background noise, indistinguishable from the sounds of birds or debris carried by the wind. The decision to rely on pattern recognition rather than raw signal strength allowed the swarm to move forward without confrontation. In a battle space crowded with sensors, perception mattered as much as detection. By the time the drones reached the far edge of the Sea of Azov, the first phase of the operation was complete, and the swarm was positioned for its transition from deception to direct engagement. The plant at Beriv remained unaware that anything unusual had occurred, and its defenses continued to operate under standard assumptions about threat behavior. This quiet approach set the conditions for the next stage, where expensive air defense systems would finally notice the swarm and respond in ways they were never designed to handle. The moment the swarm closed to within 3 miles of the Beriv plant, the balance of the encounter shifted because the long-range defenses that had been waiting in silence finally began to react. The 91N6E radar of the S-400 system cut through layers of sea clutter and background noise, and for the first time that morning, it separated the approaching objects from their surroundings. To the automated system, the 20 drones did not appear as individual machines, but as the single compressed return moving low and slow across the water. This pattern matched the profile of a low-flying cruise missile, not a collection of fragile plastic aircraft guided by human hands. In that instant, an expensive defensive network prepared to answer a threat it believed it understood. The response was immediate and decisive because the S-400 was designed to eliminate high-value targets before they reached critical infrastructure. A 40N6 interceptor was launched from its tube with a roar that shook the surrounding ground, leaving behind a bright exhaust trail as it accelerated upward. Within seconds, the missile reached speeds measured in thousands of miles per hour, driven by a system built to intercept aircraft and missiles far larger and faster than anything in the swarm. The cost of that single interceptor exceeded $1 million, a figure that reflected decades of research and industrial effort. Against it, the drones offered no armor and no speed advantage, only numbers and timing. When the missile reached the projected intercept point, it did not strike a solid target because there was no single body to hit. Instead, its proximity fuse triggered a detonation designed to destroy objects within a wide radius. The blast wave ripped through the formation, tearing 3 drones apart and scattering fragments across the air. On operator screens, 3 video feeds vanished at once, replaced by static and silence. For a brief moment, it appeared that the defense had succeeded and that the threat had been neutralized at long range. That assumption lasted only seconds. The remaining 17 drones reacted instantly, not out of panic, but in accordance with their programming. A preset evasive command scattered them outward in multiple directions, breaking the radar return into a cluster of small and irregular signals. The S-400 system, optimized to track large and fast targets, struggled to maintain locks on objects that no longer fit its engagement models. Each drone now appeared as a separate speck, moving slowly and unpredictably near the ground. The system attempted to prioritize, but its tracking algorithms were overwhelmed by the sheer quantity rather than the quality of the data. In the space of moments, the most advanced air defense platform in the region lost control of the engagement. This exchange highlighted the economic imbalance at the heart of the encounter because a single missile costing more than $1 million had destroyed only a fraction of a swarm built for a small percentage of that price. The defenders had spent heavily to remove 3 targets, while the attackers had preserved enough of their force to continue the mission. From a strategic perspective, the damage was not just physical but conceptual because the cost of defense was already exceeding the cost of attack. That imbalance would grow more severe as the fight moved closer to the factory itself. As the surviving drones crossed the perimeter of the burial plant, responsibility for defense shifted from long-range systems to short-range protection. Positioned on the roof of the main assembly hall was a Panzer S-1 unit designed to destroy threats that slipped past the outer layers of defense. The system activated its twin 30mm cannons, filling the air with a continuous stream of shells at a rate approaching 4,000 rounds per minute. Tracer fire cut through the darkness, creating a moving wall of explosions that shredded the space above the factory grounds. For the drones, this was the most dangerous phase of the approach. To survive, the pilots guided their aircraft into the industrial landscape, using physical structures as shields against direct fire. Tall smokestacks and concrete towers broke the line of sight, forcing the Panzer to adjust its aim constantly. The airflow around these structures was chaotic, causing the drones to deviate off course and necessitating constant corrections from the operators. Each time a drone emerged from cover, the system attempted to lock on and fire again, leaving only narrow windows for movement. In one case, a drone escaped destruction by threading itself through a tight gap in a massive advertising board mounted along the factory wall. The passage was so narrow that even a slight error would have had a significant impact and resulted in a loss. As this close-range duel continued, a critical observation emerged from the operators watching their screens. The Panzer system could rotate and elevate its weapons across a wide arc, but it could not aim directly upward. Mechanical limits created a blind zone above the turret, a cone-shaped space where radar and guns could not reach. This blind cone measured roughly 15 degrees, small in theory but decisive in practice. It was a flaw that mattered little against aircraft approaching from a distance, yet it became decisive against drones capable of vertical movement in confined spaces. The realization changed the nature of the engagement because the defenders were now exposed by their own design. While the cannons continued to fire outward, the space directly above the turret remained untouched. The drones adjusted their flight paths, climbing sharply when opportunities appeared and slipping into the blind zone when the guns could no longer follow. What had been a desperate effort to survive incoming fire became a calculated maneuver to exploit geometry and timing. In modern warfare, such moments often decide outcomes, not through superior firepower, but through understanding the limits of machines. By the time the Panzer crew recognized the pattern, the situation was already shifting beyond their control. Ammunition levels dropped rapidly under sustained fire, and the system prepared for a reload cycle that would soon create a dangerous pause. The drones, now aware of both the blind zone and the rhythm of the defense, held their positions and waited. This convergence of mechanical limits and human reaction set the stage for the next phase of the operation, when seconds would matter more than weapons, and the fight would move from open air into the heart of the hangar itself. As the firefight above the factory reached its peak, the surviving drones began a maneuver that shifted the entire balance of the engagement. Instead of fleeing the storm of shells, they turned straight upward. Each aircraft climbed vertically into the narrow space above the Panzer turret, a region that the defense system could not see or touch. From the ground, the guns continued to sweep outward, searching for targets that were no longer there, while the drones hovered inside the blind zone like insects clinging to the ceiling. This movement was neither sudden nor reckless, but measured and precise, timed to the rhythm of the weapon beneath. The defenders were still firing, unaware that the geometry of their own system had already betrayed them. The Panzer cannons burned through their ammunition at an unforgiving pace because sustained fire at 4,000 rounds per minute empties belts quickly and heats barrels to dangerous levels. In less than half a minute, the system reached its limit and the guns fell silent, not by choice but by necessity. Red-hot metal glowed faintly in the dark as the automated loader began its cycle, a process that required 12 seconds to feed fresh ammunition and reset the firing mechanism. 12 seconds may seem insignificant under normal conditions, yet in combat it can stretch into an eternity. During this brief pause, the sky above the factory underwent a complete transformation. It was in that quiet interval that Hangar 3 began to open. Its massive steel door lifted slowly to reveal what had been hidden inside. Floodlights flickered on, cutting through smoke and dust and illuminating two Tu-95 MS bombers resting on the concrete floor. Their long wings and silver fuselages reflected the harsh light, and for a moment they appeared untouched, calm, and almost detached from the chaos outside. These aircraft were not ordinary machines, but components of Russia's long-range nuclear force, built to survive global conflict and deliver weapons across continents. Now they lay exposed during a window measured in seconds. This moment represented the intersection of three separate factors, none of which would have been decisive on its own. A mechanical blind zone limited the reach of the defense system, an ammunition cycle imposed a forced pause, and precise timing ensured the hangar's opening coincided with the silence of the guns. Together, they created a narrow opportunity that the operation had been designed to exploit from the beginning. There was no hesitation from the drone operators because they understood that the window would close as quickly as it had opened. What followed would depend on control under pressure rather than raw speed. The silence did not last because Russian forces responded with a different tool as soon as they realized that gunfire alone could not stop the intrusion. Electronic warfare vehicles positioned within the factory grounds activated the Krasnohar-4 system, flooding the area with high-powered interference. This was not a subtle signal, but a wide and aggressive burst intended to overwhelm communication links and navigation aids. For the Ukrainian operators, the effect was immediate and frightening as control screens filled with white noise and familiar reference points vanished. GPS signals dropped out, telemetry data disappeared, and the drones began to drift in turbulent air without digital guidance. In that instant, the pilots were reduced to instinct and training, relying on muscle memory to keep their aircraft stable while the wind pushed against them. Without clear visual cues, the inner ear can deceive even experienced operators, creating the sensation of movement that does not exist. Sweat and tension replaced the calm focus of earlier phases because every correction now carried the risk of overcompensation. One drone clipped a structure and shattered, its loss marked only by a brief flicker on the screen. The electronic attack had created chaos, and for a few seconds it appeared that the defense might succeed through disruption rather than firepower. The drones, however, were prepared for this kind of assault because their design did not rely on a single channel of communication. Onboard systems detected the interference and triggered a frequency hopping protocol that transformed the radio environment into a moving target. Instead of transmitting on a single band, each drone began shifting rapidly between 900 MHz, 2.4 GHz, and 5.8 GHz, changing channels 18 times per second. To an enemy system broadcasting noise across fixed ranges, this behavior was difficult to suppress. Signals did not vanish but fragmented into brief whispers scattered across the spectrum. High above the battlefield, a fixed-wing drone serving as a relay waited at an altitude of 5,000 feet, beyond the immediate reach of ground-based interference. This aircraft collected the scattered fragments of data sent by the swarm and assembled them into a coherent stream of information. Rather than sending the signal back through conventional radio paths, it transmitted the info using a narrow laser link aimed directly at the control station. This method produced no broad emissions for the jammer to target, and it slipped through the electronic fog unnoticed. The defenders continued to pour power into the air, unaware that the conversation had moved beyond their reach. As the interference lost its grip, the video feed snapped back into clarity, restoring high-definition images just as the hangar opening reached a critical width. The pilots inhaled sharply, regaining situational awareness just when they needed it most. The scene inside the hangar came into focus, revealing aircraft outlines, equipment carts, and personnel scrambling in confusion. The electronic battle had been decided in seconds, and its outcome favored adaptability over brute force. Control returned, not because the interference weakened, but because the drones had learned to ignore it. With weapons temporarily silent, communications restored, and the hangar now open, the operation entered its most dangerous phase. The fight was about to move from open air into a confined industrial space where heat, fire, and shock would decide the fate of the bombers. As the surviving drones crossed the threshold of Hangar 3, the air itself became an enemy. The enclosed space trapped heat, dust, and violent currents created by the moving machinery and rising smoke. The 10 aircraft pushed forward through this unstable environment, their small frames shaking as turbulent wind bounced them off invisible walls of pressure. Inside the hangar, sound echoed sharply, turning each engine note and shouted command into a disorienting roar. The pilots had no time to adjust slowly because every second inside this space increased the chance of collision. Control now depended on precision and restraint rather than speed. The drones ignored the massive bodies of the bombers at first, a decision that reflected careful planning rather than hesitation. Their true objective sat closer to the floor, mounted on a wheeled cart near the aircraft wings. This cart carried industrial oxygen tanks used for welding and structural repair, as well as cylinders designed to release controlled flows of gas under safe conditions. In combat, however, those tanks represented stored energy waiting for ignition. By striking here, the attackers aimed to turn the environment itself into a weapon. The lead drone accelerated and impacted the oxygen cart, triggering a shaped charge designed to focus energy rather than scatter it. The blast did not simply rupture metal. It released compressed oxygen instantly, creating a superheated jet that burned hotter than most conventional fires. Temperatures climbed beyond 3,500 degrees Fahrenheit, producing a cutting effect similar to industrial plasma tools. Sparks and fragments filled the air as the jet punched upward, seeking the nearest source of fuel. The hangar became a furnace in less than a second. Directly above the oxygen cart stretched the wet wing of the Tu-95, a structure that carried nearly 20,000 gallons of aviation fuel. Under normal conditions, this fuel resists ignition and requires specific triggers to burn. The oxygen jet completely removed those protections, melting the aluminum skin of the wing almost instantly. Liquid fuel flashed into vapor and ignited in a violent expansion that lifted debris and bodies off the floor. The explosion was not sharp or brief, but heavy and sustained, pushing heat outward in a rolling wave. Fire spread along the aircraft with alarming speed because components designed to withstand cold and high altitudes offered little resistance to the intense heat from below. The bomber's landing gear tires, each weighing hundreds of pounds, caught fire and began to burn with thick, black smoke. This smoke filled the hangar, reducing visibility to almost nothing, blinding defenders and overwhelming the ventilation systems. Breathing became difficult as toxic fumes pooled near the ceiling and rolled outward through open doors. The interior temperature climbed rapidly, turning the hangar into a sealed chamber of flame and pressure. As the first aircraft burned, another drone struck deeper inside the hangar, aiming for a maintenance rock holding Kh-55 cruise missiles awaiting installation. These missiles were training variants, yet their solid rocket fuel remained intact and highly energetic. When the drone detonated, The casing of the first missile split open and the propellant ignited. Because the rockets were clamped in place, the energy could not escape through forward motion. Instead, it released as pure heat and pressure, transforming the rock into a stationary bomb. The heat from this ignition reached levels that softened concrete and warped steel, leaving scorched patterns across the floor beneath the rack. The structural elements of the bomber began to fail as the aluminum lost its strength under sustained exposure. The wings sagged and twisted, no longer able to support their own weight. With a grinding sound that cut through the roar of the fire, one wing collapsed and tore away from the fuselage. The aircraft that had once carried nuclear weapons across continents now disintegrated under forces it was never designed to resist. The collapse severed fuel lines and spilled remaining fuel across the hangar floor, feeding the inferno and expanding the burn zone. Flames reached engines and support equipment, igniting secondary fires that merged into a single massive blaze. The NK-12 turboprop engines, enormous and complex, broke loose and crashed onto the concrete, crushing maintenance platforms beneath them. Each impact added shock and vibration to a structure already pushed beyond its limits. The hangar shook as if an earthquake had struck it. The final phase of the attack unfolded as the 6 remaining drones lined up for their terminal runs, targeting the engines directly to ensure destruction. These drones accelerated to maximum speed and struck almost simultaneously, delivering shaped charges that focused energy into narrow jets of molten copper. These jets traveled at extreme velocity, piercing hardened steel casings and shattering internal components. The combined impacts generated intense overpressure inside the hangar, exceeding 60 pounds per square inch and overwhelming the structure's design limits. Under this pressure, the hangar roof failed, peeling back as if forced open by an unseen hand. Corrugated steel panels tore loose and were thrown upward, releasing a towering column of smoke and fire into the morning sky. The plume rose more than 500 feet, visible across Taganrog and beyond, marking the end of the Beriev plant as an operational facility. As debris settled and flames continued to burn, the drones withdrew, or were expended, leaving behind a site reduced to twisted metal and ash, setting the stage for the final assessment of damage and strategic consequences that would soon follow. 8 hours after the first flames erupted inside Hangar 3, the Beriev aircraft plant no longer resembled a strategic military facility, but a silent field of twisted steel, collapsed roofs, and blackened concrete. Fire crews continued to work through smoke and heat. Yet what remained was no longer salvageable because the core of the factory had been burned beyond repair. For Ukraine, the total cost of the operation was modest by military standards, estimated at roughly $240,000 when accounting for the drones, the airborne relay, and the intelligence effort that guided them. That figure stands in stark contrast to the losses inflicted. Russia lost two Tu-95 strategic bombers valued at approximately $90 million, along with specialized infrastructure and tooling estimated to be worth an additional $50 million. More damaging than the numbers on paper was the time lost, because according to CRI 2025 data, the Beriev plant had roughly 18 months of strategic bomber modernization capacity. In a single morning, that future was deleted. When measured purely in military return, the operation produced an estimated return on investment of nearly 58,000%, a figure rarely seen in modern warfare. The more profound message of this strike extends beyond the realm of accounting. Modern conflict no longer requires matching an enemy dollar for dollar, platform for platform, or missile for missile. It rewards flexibility, software, and the ability to capitalize on small human mistakes within large systems. A handful of inexpensive drones guided by artificial intelligence and patient planning proved capable of disabling assets designed to anchor nuclear deterrence. The question now is how this lesson reshapes the future. If strategic bombers can be neutralized by tools once considered improvised, what does that mean for nuclear security in an era of cheap autonomy?